Excellent. So last lecture, we have really been delving deep into the shell lab, walking through the implementation and talking about those system calls and those helper functions that motivate for us what goes into building a shell. And so we kind of learn these new concepts as we come to grips with having to implement a new feature into our tiny shell. So I do want to highlight that I think in one of my slides while I was converting my code into these walkthroughs, there was a mistranslation error that didn't affect our traces while we were testing, but they will affect us in future traces. And I'll be honest, I was beating my head against the wall using because I wanted to walk through what we're going to do today. And I have some test code I played around with. And for some reason, the code we wrote in class just would not work with my tester code that I had built the slides off of. And it's because this function here, well, I'll have to go ahead and correct this. This function to add a job, we want to add a job regardless of if it's a foreground job or a background job to our jobs list, right? I had accidentally put that instruction inside of this else clause when we were first implementing this. So we don't want to do that. We want to add every job to our job list. That's going to cause an issue for us if we don't do that. So make sure that this line of code, add job, I have to do it myself too. But make sure that this happens before we check. So it should be the first line inside of the parent process. We're going to add that job, and then we're going to decide what to do if it's a background or foreground job. So that could just be a simple cut and paste. And I'm going to do that right now. So let me go here. And again, for those in class, if y'all are also either on Discord or on Zoom, if anyone asks inside of the channel, please let me know, because I'll be, for the most part, playing around inside this environment. Okay, let's see here. So we're in Shell Lab. Let me open up a terminal. Perfect. We have a terminal. And let me also, let's go ahead and open up our Shell Lab code. Okay, so let me do that same change that I just said that you all had to do so that you can see exactly where this is happening at. So I'm going to go back towards my eval function right here. And we will cut this. Also, what is going on here with my formatting? It is all crazy. Let's get our formatting under control. Okay, this is what I commented out last time. I'll leave that commented out. I'll just remove it entirely. Let's get that there. Okay, let's get here, here, here. And let's move this here where it belongs. Oops. Okay, perfect. Let's save that now. And now let me jump to my terminal and make sure that everything is working, and we'll pick up where we last left off. So if I go here and we compile, so compile our code. Okay, oops. Reverse my, there we go. Okay, let's see here. Let's clear this for a moment. GCC tsc.c, that's, let's see, no such file. Where am I? No such file. As tiny shell, I see. CSC. Where's my C code at? Wait a second. where did my tiny shell code go? Oh, that's not promising. Did I delete it? Well, let's see here. Okay, well, let's just do this. So inside of here, I have that there. Okay, let's try this again. Okay. Somehow I must have accidentally deleted it, but fortunately, since it's open in my text editor, I can just resave it. Okay, so let's test this out. Oops. So we successfully got trace 1. We successfully have trace 2. We successfully have trace 3. We successfully have trace 4. And I think this is where we last left off, right? And so good. So now we see right at trace 5. That's where we last left off. Perfect. So let's clear out of this. So we're right back where we started then. We close this, and we'll just have open our code and our terminal. Perfect. Okay, so the first thing we want to do, let's go back to our slides then, and let's go walk through. We're done trace 4. Okay, so that means we can move on to trace 5. So if we're going to move on to trace 5, let's find out what the motivating feature for trace 5 is going to be. So we can see here our goal is listed in the header comment of all of our trace files. Here it's going to be able to process jobs built-in command before and after jobs finish. So up to this point, we only have the one built-in command as a quit. Is that right? We haven't implemented any other built-in commands yet for our shell. So this is the first time that we're going to build in another built-in command that actually does something meaningful beyond just exiting out of our application. So we can actually see what's going to happen. If we look at the trace file, we can see we're going to call on that external application to my spin for 1 second in the background, right, with the ampersand. And then we're going to do that again to have another background process for 3 seconds. And then we're going to call jobs, which should list the set of jobs. Then we're going to go ahead and sleep for 2 seconds and call jobs again. And then we're going to sleep for 2 seconds and then call jobs again. Let's see what the expected behavior is going to be. In fact, we can actually look at the expected behavior. I think I improved these in a moment. So let's just jump into here and we'll actually examine it. So let's do make our test 5. And here, there we go. Okay, so we can see we have the call to myspin 1 and myspin 3. And then we could see when we call jobs, it's then going to report what jobs are currently running at each of those instances. So let's compare this output to what our output from our application is. It should be quite evident what it's going to be because we don't have a jobs command, but we're going to do it anyway. Oh, we did implement jobs? Oh, yeah, me too. We must have done that as 4. Was that what the last thing we did was? However, we can see that there's an issue with our output. So yeah, I think actually jobs was the trace 4 that we implemented, but clearly something isn't working for us correctly, right? We can see that we are properly spinning up that background process. That's the first piece of output that we see when we invoke that. Remember that prints message to the screen. We're doing the appropriate thing on the second. And then what's happening here is look at all this right here. Running. Whereas here, so looks like we're double printing. Is everyone else getting the same thing? Okay, and let's see here. And let's see what this says here. So our observed behavior is the myspin command starts as expected, but the jobs command output does not reflect the current job statuses correctly, listing the jobs as running that should have completed. Okay, let's talk a little bit with this one in terms of our Unix signals, because this is the first time we're really going to start delving into signal handling from our shell. So signals are a form of inter-process communication in Unix systems that are asynchronous notifications that are sent from a process to inform of various events that can occur. So these next couple of traces are really going to have us start exploring the signals and how we can capture the signals and do things in response to signals. So there are various types of signals, such as the interrupt signal. They have the kill signal. They have the child process signal. In terms of default actions, each signal has a default action associated with it, which could be used to terminate a process, ignore the signal, or catch it to perform a specific function. So we have custom handlers that are defined inside of our tiny shell. And in fact, those are things that we'll have to implement. If I go down past the core set of functions, you'll see they have some signal handler functions right here. But right now, they're completely left blank, right? I have a SIG child handler, which is simply just stubbed out with a return statement, SIGINT handler, and our stop signal handler as well. So our interrupt, our child process, and our stop signal handlers. So we're going to have to start exploring these, I think, in order to start accomplishing this next trace. So, of course, the purpose of this trace really, and the ones that are coming forward, is for us to start getting a better understanding of these Unix signals so that we can build our shell in a way that allows us to manage our processes and have concurrent sets of processes going at one time, but also manage the state of what those processes are inside of our jobs list. Okay, so let's take and examine some of the code that's given to us. So again, as we implement our source code, it behooves us to examine some of the helper functions and some of the data structures that are provided. So one of these is the signal function, which is a wrapper for the SIG action system call. It's setting a signal handler for a specific signal and ensuring that interrupted system calls are restarted, returning the previous signal handler. So here you can see we have this data structure that we will go ahead and utilize. And so just to give you an idea of what signal is wrapper class for, again, there's a system call SIG action, which takes the form of this usage. Now, we don't have to use this directly because signal is wrapping around this implementation, but this just gives you a little bit of information about what the underlying implementation is from the system level. And again, a good purpose of what this slide intends to motivate is that SIG action provides a comprehensive and reliable mechanism for our signal systems, and we're wrapping around that, which is, and then this code right here is actually in your tiny shell. Now, why am I emphasizing this so much? Because if we go into the very beginning, I know normally highlighted code is changes. This is just to highlight what we're actually going to look at for this implementation. So if we look at the very beginning of the main function, we can see that these signal, the wrapper class is actually being utilized in the very beginning of our main function to bind certain signals that couldn't occur inside of our shell with a callback function, which is going to be our specialized signal handler. So the idea is the reason why we implement our code to handle a signal in these functions is because we're binding this callback function towards getting invoked whenever that signal occurs. Does that make sense? Okay, just making sure everyone kind of understands what the concept of a callback function is and what this code is doing. And again, just to highlight where this code is in particular inside of our actual code base, if I was to scroll down towards my, here we go. So if I scroll down to my main function, I can see right here, this is where we install all of our signal handlers, right here. So these callback functions are being set up by that wrapper class, which is now doing that binding. So we can create custom signal handling. Okay. So the idea is that as we keep exploring this, we understand more and more of what the code that's provided for us is doing. It's going to be important if we're going to successfully implement the parts that are missing. Okay, so the particular signal we're most interested in for this implementation, for this trace, is going to be our sig child in shell. So sig child is the signal that's sent to a parent process whenever a child process terminates, stops, or continues. Right now, that signal is being triggered, but we're not doing anything in response to it. And since we're not doing anything in response to it, we're getting the duplicated printouts because we're not updating what's happening inside of our jobs list effectively. Okay, so obviously the purpose of our signal child handler then is it's designed to catch and respond to the sig child signals, allowing the shell to update the job list and state our information correctly. So of course, the functionality we're going to care about is when it's invoked, it's typically going to use something like a wait function to fetch the termination status of the child process that has changed state, ensuring that the shell's job list accurately reflects the current state of the background or the foreground, which is what we're not doing yet. Okay, so let's move on. Okay, so what is the process by which we're going to implement? Well, we need to check for each shell process that there is. We need to get the status of that child process without blocking if no child has existed. Check whether a child process has changed state. And if a child process was terminated by a signal or exited normally, remove the job from the list. Let's focus on this. We're not worrying about termination. Let's just say if it exited normally. We'll worry about termination due to a signal, like an interrupt signal for future trace. So I'm going to edit that just to say we care about whether we've exited normally or not. Okay, so with that said, here are some, and you know what? Let me do this. I'm going to cut that. I'm going to duplicate this in real time. We're going to paste this here. Okay. Trying to declutter some of these slides. Okay, so we know what the general purpose of what we're going to do in our sig child handler function in terms of pseudocode. So obviously the new actions that we're going to do are going to line up nicely with our pseudocode. So inside of our sig child handler function, we're going to do the wait PID function to check the status of a child process. And then the status is going to be determined based off of how that process, whether it ended or not. And if the process did end, then we are going to call a helper function, delete job, which will then remove that process from our job list. And so this loop should continue for any additional child process that might have changed state. So the key system functions we care about here are going to be wait PID, which suspends the execution of the calling process until a child specified by our process ID argument has changed state. And then we also have this macro that checks the exited state of our child process. It'll return true or false, whether, well, it was true or false, that it exited or not. And then one of the key helper functions that's built into our source code file that we can make use of is a delete job function that's going to delete a job based off of a PID. Now, let's just look through very briefly each of those critical system calls or helper functions that we might care about. So wait PID, we could see the purpose that we're going to use, at least in our shell development, is to wait and gather the exit status of a child process. And so here we can pass in a status, and it's going to return true or false on whether the status that was supplied to us is consistent with this use case. So here, a non-zero value if the child terminated normally, such as calling to exit or whatnot, just because it got complete to its main function, and it would be false otherwise. Okay, so with that said, we also have the delete jobs function. This isn't something that we have to implement ourselves, but it's good to know what it does. So we can see here that it'll iterate through our job list to find and remove a job with a given process ID, updating the next job ID if successful. So this will allow us to now remove jobs that are complete. Okay, so with all that said, what is the actual implementation? So recall, we already have a SIGChild handler function. What we're going to want to do is implement it in the following way. So we're going to start by setting up the data that we might need for this particular function to operate. So we'll need a child PID. We need to track the status, which we'll provide a reference to, and then it'll get updated so that we can check it in future checks of our function call. And then finally, this is our loop control variable. Do we have another child, has next child effectively to step through to iterate through this process? So while we have more children processes, we're going to do the following. We're going to go ahead and wait for that child, state to change and grab its status. So now we will now have that PID. Then we'll check to see if there are more children processes after this one. So if our child PID is greater than 0, then that means there's going to be more processes. So then we'll set our loop control variable based off of that has next to determine whether we're going to do another iteration of this loop. And now we're going to start responding to the status. So we're going to call that macro. If it exited normal, we're going to give it that status. And if it's true that it exited normal, then we're going to delete that job using that helper function from the job list. Is this pretty understandable in terms of what this is doing, what system calls it's making? Okay. Well, let me implement it as well. So let me jump over here, and so I'm going to go to where my signal handlers are at. And it's right here. In particular, we're going to do the signal handlers for the child process. And we can read the description. I don't know if I formally did that. Let's read the description so we know in the future what the role and responsibility of SIGChild handler is. So the kernel sends a SIGChild to the shell whenever a child job terminates, becomes a zombie, or stops because it received a SIG stop or a SIG stop signal. The handler reaps all available zombie children, but doesn't wait for any other currently running children to terminate. So that is the role of this particular function. Okay, so let's start with the data that we will need over the course of the function of the life cycle of this function. So here we will have a child PID. Here we will have a status. And here we will create a loop control variable that we'll just call has next. And we will initialize it to 1. Okay, so while another thing that you'll see, I'm pretty fanatical about loop control variables. I hate having expressions inside the body of the evaluation of where loops occur at. I like readable variable names that get updated inside the body. I think it's integral to readable code, literate code. Okay, first let's go ahead and get that child PID. So, oops, what is going on here? Okay, so our child PID, we were going to make that call to that system call to wait PID. And here we're going to supply it with the arguments of -1, the address of our status variable. And for this instance, we will do no hang. We'll update that with untraced as well when we get to the interrupt signals. Otherwise, that's going to cause us an issue, but I do like to see when those issues crop up. That way it motivates when we have to add in new logics for things that behaviors we're trying to capture with our shell. So I try to be bare minimal with each step to try to identify what we then have to add because it results in erroneous behavior. Okay, so that should grab us that child process. Then based off of that, we can determine the new state of our has next, our loop control variable. So on the instance that our child PID is greater than 0, we'll determine whether we're going to loop over again. And then what we'll do is if, now we're going to check this exited state, and this is going to require the status to be passed. So if that is true, that this exited normally, then I want to do, in response to that, what is expected. So in this instance, it's to remove that job. So we have that helper function, delete job. And so inside of delete job, we pass it our jobs list. We pass it the child PID to go ahead and do that. Excellent. So let me save that. So now let me jump over here. Let's clear this. Oh, yeah, let's clear this. And the first thing I'm going to do is let's go ahead and recompile our code. And let's do, this is we're on trace 5, right? So let's see what our reference, let's see. Okay, and now let's also do our reference to compare the output. Okay, this looks much better, right? We've now successfully managed deleting the jobs after they've normally exited. So now our reference shell and our implementation are in line. So let's double check that we're done with this trace by just running our check. So we've successfully completed trace 1. We've successfully completed trace 2. We've successfully completed trace 3. We've successfully completed trace 4. Hopefully, yeah, there we go. We successfully completed trace 5. Fingers crossed. Yep. And now we should fail at trace 6. Perfect. That's exactly what we want. We always want to be failing at the next trace because we didn't intend to implement ahead of time, right? We're purposely minimally implementing to motivate what the new code is that our shell is going to require to manage those new responsibilities. So let's jump here. And so we can see we've successfully done this. We've verified our implementation. So let's move on to trace 6. So in trace 6, what is going to be the new thing we're going to try to do? Well, we're going to try to run 2 background jobs and 2 foreground jobs. So we can see if we look at what the tester is going to try to do, it's going to execute that my spin program for 4 seconds in the background. Then it's going to go ahead and call ls. So as a foreground process, and then it's going to do my spin for 2 seconds as a background process. Then it's going to call ls again as a foreground process. Then we're going to call jobs. And then we're going to sleep for 5 seconds and call jobs again. And finally, we're going to quit. So let's take a look. Yeah, this is where I think the slides get better at us being able to evaluate between the expected behavior and the observed behavior. So I'm going to run this in the terminal, but what we should highlight is that with our expected behavior, we're going to get the echo, the description of our trace 6. We're going to get a message that job 1 with some PID has initiated. Then we'll get the output from our ls. So it's going to just spam our screen with all sorts of file names. Then we're going to get a message that job 2 has initiated. Then we're going to get a second output from our call to ls, which is going to just spam our console with all sorts of directory names and file names. Then finally, we're going to get status of job 1 and 2 displayed. Now, jobs 1 and 2, right? Those are going to be our background jobs. See how I have job 1 and 2. What we're going to see in our observed behavior in the current implementation that we have is we're going to get the description of our trace 6. That's fine. That means that's working as anticipated. We're going to get the initiation of job 1. Okay, so far, that's the same. But then we're going to go and output from our bin. That's fine too. That's what we should have. Then we're going to do an initiation of job 3. Of job 3, which notice it's labeled as 3 and not 2. So that's going to be distinguishing different things because we don't care about PIDs, but we do care about job IDs. So that's already a difference. Then we're going to do our second output of ls, which is going to be the same. And so here, one thing I should do then is I should highlight the things that are different. Just so that is different. And this last bit, when we go and run this, we're going to see is going to, nope, don't do that. Do this one. Okay, perfect. Then it's going to display the status for our jobs, and it's going to show 4 jobs. It's going to show the foreground jobs and the background jobs. We don't want that. We want to display just the background jobs. So let's take a look. Let's see, and just do that comparison, like I said. So I'm going to make the reference test, and this is test 6. So that's the echo of our comments, the description. Oh, and now let me scroll up so we can actually really see. And then we see, okay, yeah, then we see job 1, right? The background job, and then the display from ls. And then we could see here, job 2, background job, and then ls. And then we can see that job 1 and job 2 are part of the jobs output. Okay, let's compare that with what I said our current output should be. So we have the echo. And we have job 1. We have the ls. So far, this is the same. But now notice here, yeah, instead of being job 2, this is labeled as job 3. So that's a big difference. Then we have our ls. And then this is the biggest output, is showing all the different jobs, foregrounds and backgrounds. Okay, so now we have a clue as to what has to update. Something isn't quite right with the way our jobs command is working. So we're going to have to refactor that. We're going to have to fix that. Okay, so what we're going to have to do is what we had done previously. I want to say way back in like trace 2, we had implemented the wait for foreground process to be very simple. It just waited for that one basic process to return back, and we just used wait PID on that. And so wait PID is it's a blocking call, and it's fine. It's fine for when we do signal management stuff, but we're going to want to do something a little bit differently. The problem is when we called wait PID, we didn't do anything with the jobs list, right? The jobs list was this abstract thing. We're just like, what is a good way for us to pause for the foreground process to finish terminating before we go ahead and return control back to our application? Because remember, if wait FG was used so that our shell wouldn't display the prompt before displaying ls. Do you remember how that was an issue way back in Trace 2? And we just did a very simple, easy implementation. Well, now we have to think deeper about this. Now, when we're waiting for the foreground process to complete, we should update our job list, or we should wait on our job list, or we should be more consistent with our job list accuracy. Because the job list is how all of our helper functions are maintaining what's running, what's stopped, right? We're going to track that inside of our job structures. So what we're going to do is we're going to update wait FG to retrieve a job using its PID from the jobs list. And so we want to evaluate in our jobs list, what is the foreground job? We're going to exit if there's no corresponding job. But if there is a foreground job, we're going to use sleep to implement a non-blocking wait for it. So just some key features, we're going to use a system called sleep, which just temporarily suspends the current process, enabling other process to execute. And we're going to use a helper function that's given to us inside of our tiny shell code, get job PID, which is going to find a job by the PID on our job list. So this is just the API effectively for our system call of sleep. The big thing here, you can see we can pass it some number of seconds. It will return 0 if the specified time has elapsed, or the number of seconds left to sleep. In our development, sleep is going to be used to pause the execution of our program for a specific duration while we wait for our process management to go ahead and do what it needs to do. So again, I just want to reiterate and examine what a job looks like. So recall that a job has a PID, a job has a JID, a job has a state, which is what we're interested in. Is it a background job? Is it a foreground job? Is it a stop job? Is it an undefined job? And then we also have the command line. And so get job PID then is, given our jobs list and given a PID, it will search that array and return back the job from the job list that matches that PID. Yeah. Okay, so with that said, setting up the helper functions we're going to care about, setting up the system calls we're going to care about. Let's see how we can reauthor our wait FG function to be more compliant with managing multiple jobs at a time, so that we don't just hoard jobs without doing things and result to that. So the first thing I'm going to do is I'm going to grab the, I'm going to get past a PID. I'm going to use that PID to grab a job from the job list. If there's no job, I'm just going to return out. If a job doesn't exist, we're done. If a job does exist, that means that I can access its PID, and if it's equal, and if the state of that job is a foreground job, then I'm going to tell the system to sleep. I'm going to tell it to keep doing that until that job has been completed. So here I'm actually going to wait, where we weren't actually doing waiting before. Not like this, not not where we can actually start iterating through the job list. Before, it was just whatever the last process was. This allows us to start managing multiple processes, which is, of course, or multiple foreground processes, which, of course, is the point of this particular trace. Okay, let's implement this and see. So let me go into my, so it's going to be up here. It's right here. So this is my current implementation. So I'm going to go ahead, and that worked for trace 2, but now it's time to refactor. Okay, let's see here. Let's go ahead and get ourselves, nope. Okay, perfect. And get job PID. Oops. And inside there, we're going to pass in our jobs list, and we're going to pass in our PID. And then we're going to check if we don't have a job, we're just going to return. And of course, there's many ways I could have done this. I got to check for its existence and done the while loop. This is fine. And then if we got this far, then that means we do have a job. Let me get my loop of body here. So from my job, I want to access its PID, and I want to see if it's equal to the PID that was matched in. So while that's true, and on this job, I want to access its state, and if its state is equal to a foreground state, then I want to sleep. Excellent. Okay, let's jump here. Clear that out. Okay, let's compile this. Oops, what did I do here? Wait, FG, am I missing? Did I? Okay, let me just look at the instruction. Okay, let's see here. Oh, semicolon. Okay, perfect. And now let's go ahead and check our output. So I'm going to do make on test 6. And so here we'll have to scroll up just to confirm that is what we would want it to be. Oh, I can already see that the tail end looks fine. So just based off of that, why don't we just run the checker? And so we pass trace 1, we pass trace 2, we pass trace 3, we pass trace 4, yeah, got through trace 6. Okay, so the next one, we should fail on trace 7. Excellent. Okay, so notice here, let's move on then. You're happy that we got through a trace. So let's see what the next piece of functionality is. Oh, let me see some of the messages too. Oh yeah, you bring up a good point. So I'll probably supplement some slides with a with some of the concepts that I'm trying to add in all the slides as it motivates, but yeah, I might clearly miss some, such as these concepts with no hang or with untraced or whatnot. So as that comes up, I'll probably supplement with the slides. And I actually have to get these slides too as well, so everyone has access to these slides. Thank you for that comment. Okay, let's see here. Let's see, the next trace, if we go and examine what the comment says, is we want to go ahead and forward a interrupt signal to our foreground. So right now you can see this is relatively simple in terms of what we're doing. We're going to set up a call to MySpin as a foreground process for 4 seconds. Then we will sleep for 2 seconds, and then we will interrupt that foreground process, which should terminate it, right? And in fact, let's see what happens with the expected behavior. We'll actually test to see what ends up happening there. So we can see if we make our reference test, it's going to have 2 pieces of output from the reference shell. It's going to echo that header comment, and it's going to say job 1 with some PID number was terminated by signal 2. And so if we go and try to make it with our current implementation of our shell, it's just going to echo the header comment because we're not handling interrupt signals at all, right? That's just an empty return statement. So just to verify that this is where we're at, let's make our test 7. Yep. And now let's remove the R for reference. So it actually just test R's, and we can see, yeah, it's just that trace 7. Notice it took a little longer to complete because we had to wait the 4 seconds for our application to run to completion before we finally came out. Whereas this, after 2 seconds of sleeping, it automatically interrupted it. So what is the general process by which we can go ahead and capture that interrupt signal? Well, we have to implement our interrupt signal handler, our SIGINT handler. So effectively, what we want to do is we want to retrieve the process ID of the current foreground job from the job list. And if a foreground job exists, we want to use the kill function to send a SIGINT signal to terminate it. So some new actions for this particular trace, which is trace 7, is to implement our SIGINT handler to correctly handle the SIGINT signal to terminate our foreground process. And again, another way to send this interrupt signal from the keyboard would be like hitting Control-C. Okay, so just some highlights on the functions that we're going to use for our implementation. In terms of system functions, we're going to use the kill function. That's going to send a signal to a process or a group of processes, typically used to terminate or otherwise signal processes. And we also have a helper function, FG-PID, foreground PID, which is going to retrieve the PID of the current foreground process, or 0 if there's no foreground processes. So again, just to take a quick look, and we can see that in order to call kill, we have to supply it with a PID and a integer, which is the signal, the type of signal that we're sending. We're going to use the kill function multiple times, but we're going to send it different signals, and we're going to handle those signals differently. And it's going to return either a 0 or a -1. 0 is a success, -1 is some error. So again, the reason why we care about kill is it's used to send signals to processes, which can instruct them to either stop or continue or terminate, depending on what the action is. So we're generating those with our signal handler, which will then be responded by our SIG child handler, which will then capture that signal, evaluate it, and then report to the user and update the state of our jobs list. So all of the management of the jobs will actually be done by, so that's going to become a relatively big function. Okay, so So this is just one of the helper functions. This is the foreground PID. We can see it's what it does is it just iterates through the job list to find and return the process ID. But I always think it's beneficial just for you to actually tangibly see these helper functions that we're going to make calls to. Okay, so what's the implementation that we're going to use for our SIGINT handler? Well, the first thing we're going to do is make a call to that helper function. So we're going to pass it the global variable of our jobs list, and it's going to return back to us a PID, which is, remember, it's 0 if there's no foreground process. It's non-zero. It'll be some positive job number because we start counting up at 1, right, when we've seen our job list. So if our PID is greater than 0, then we're going to go ahead and we're going to kill it. Now notice we're doing something, we're going to call that kill function. Now notice we're doing something pretty interesting here with this kill call. We're prefacing it with a minus sign. And that's because we can use the kill function to signal an entire group of processes when we use a negative value. And that's what we're going to want to do. We're going to want to go ahead and we're going to see. Well, I'm actually going to play around to show you what happens if we do it just for the PID directly or whether it's a process group. But the appropriate way to do this is to do a process group, but then we have to define a process group, which we'll update our eval function to do. We haven't done that because we weren't doing any signal handling, but now that we're talking about signal handling, typically it's better to do it with our groups of processes instead of our individual processes. So this is one thing. And again, the idea is we'll play around to see what the behaviors are. So don't let me not get through this trace without doing that. So I'm interacting. And then here we also are going to use SIGINT as the state of what we're going to pass. Oh, so let me actually go in here and implement this. So I'm going to go into here, SIGINT. I'm going to grab that, and if the PID is greater than 0, we're going to call that kill function on the negative value PID and with SIGINT. Excellent. Now, potentially, I could also put, I'm not supposed to, but just to illustrate how the flow of all this is working, I'm going to put a test comment in here just so you can see. So I'm going to do this. But this isn't going to stay here. This is for testing abilities because this isn't really the responsibility of the interrupt handler. But I'm going to put a flush print formatted call. I'm flushing it because when we're handling the signals, we want to flush the buffer to ensure that it actually prints out. So since I'm going to do this, I'm going to go ahead and pass it what I'm flushing to, standard out. I'm going to pass it the formatted string. So let me do something like job %D. Let's say, so that's my job number, that's my process number, and a comment, something like terminated by signal, and then I'll do %D and new line character, and let us pass in this PID to JID, and then pass it in our PID. Let's pass it in our PID, and let's pass it in the SIG, which is our parameter here that gets passed in here. Okay, let's just see what happens when I do this. And actually, what happens if I leave this minus sign out right now too? Let's just see. I'm gonna jump on over here, I'll clear this. Okay, let's go ahead and make our test 7. And clearly, we're just hanging, not getting any printouts. Okay. So the next thing we're going to do is return this back. And let's jump here. So what else do we have to do? We have to go ahead and we have to update the signal child handler, which I will do, but let's jump back to this. We're going to jump back to this one really quick. I want to jump to having to update our eval. Okay, so we had mentioned that in order for us to go ahead and set the child process to a new process group so that we can handle our signals appropriately, inside of our eval function, what we want to do is call this system function set PGID. That's our process group ID, which requires a PID and a process group ID number. So what we're going to do here is, in order to set this up, is we're going to update one line of code inside of our eval function. We're going to call set PGID, our process group ID, on our child process, which when we go and fork is going to be 0, and then we're going to make it process group 0. So I'm going to do that too. Okay, so inside of where I want to guarantee that my PID is equal to 0. In this instance, we're going to go ahead and call that set PGID, and the two parameters I'm going to set are 0 and 0. We save that. Just out of curiosity, let's see what happens if we go ahead and try to call that now. Still hanging. Let's clear this. Also, let's go here. Okay. And then make sure that, okay, so here set, yeah, that looks good. And here we have, that all looks fine. And here we have here, perfect. SIG handler. Okay, we're going to update this in just a moment. And here we are pulling our PID. Thus, if PID is greater than 0, we're going to go ahead and kill that. Okay. So the next thing I want to do, let's see, that's perfect. Let's finish implementing what we want. Which actually, though, I want to make sure that everything is working up to this point. SIGINT PID %D line. Here, let me just pass it PID. Save that. Okay, oops, I gotta put standard out. So. And forget my stream on which to bind that to. Okay, format string. Looks fun to me. Oh, here. There. There we go. All right, you know what? Well, this is fine here. That's fine there. There. Be getting job. I should be getting a ping there though. We can finish implementing this in just a moment. That'd be nice. Let's check reference. Yeah, perfect. Okay. So let me go to my child process. We'll finish out this implementation, but we might be doing a little bit of debugging. Set PG. But I do want to get through the final implementation before we get through. Oh, gotta go backwards. Okay, so let's go here. So I skipped ahead a little bit. So we first looked at our SIGINT handler. And I wanted to show just doing some basic printouts, but we'll take a look at that in just a moment. And the next thing is we stated that is actually going to be the signal child processor that's going to be responsible for monitoring the changes for the state in the child processes. So if a child process was, say, for instance, terminated by a signal or removed it from the list, then we want to do something in response to that. So this is going to be a function that's going to grow. So we're going to see, we are going to have this macro that returns true if our child process terminated because the signal was not caught. And then this macro is going to return the signal number that caused the child process to terminate. So that's going to allow us to get the display we want. And again, the helper functions we're going to need are going to be the delete job and then this PID to JID function call that converts our process ID to a job ID. These are just the macros. And this is the delete job, which we've seen already. So let's do this one last implementation. And so in this implementation, you can just see, we've already checked to see if we've exited the status. And if it was a normal exit, then we delete the job. If it wasn't a normal exit, if it was a signaled exit from, like, say, for instance, Control C, then the first thing we're going to do is we're going to grab the job ID, and then we're going to try to delete the job. On a success, we're going to try to print that statement. And the statement's going to print with the JID, the PID, And then we're going to use this macro that we can send it in the status we're giving that's going to give us the signal number for it. Let me actually implement this. There we go. So inside of here, if we have our okay, so on this instance that we are got the signal for an interrupt, then I want to grab the child JID, and I can grab that with PID to JID. We're going to pass it in that child PID. Then I'm going to go ahead and grab the success on the attempt to delete job. And here I'm going to pass it in the jobs list and then the child PID. And then here, if it was successful, if it was a success, then I'm going to do this print F standard out. Actually, let me just copy this over here since I already had done this once before. Let us go ahead and effectively print this out. Now the difference is this will be my child JID. This will be my child PID. And this here will be my terminate signal. And then I'll pass it in my status. Okay, perfect. Let's save this. Oh no, cancel. Let's go ahead and save. Comment out this line, don't need that. Okay, and then I already have where I'm trying to do this process group here. Trying to grab that foreground job, that looks fine to me. And let me just double check to make sure that I did set up my process group ID inside my eval. So it's, let's set process group ID. Let's make sure everything's saved. And let's just see if we can compile. Oops, going to need to correct that. Okay, let's see here. Right there. Status. Okay, it was. Save that. Jump here. Clear. Let's see if we'll have luck. I don't think. Oh, there we go. So at this point, and this is where it gets really weird, there's no way for us to get through trace 8 without getting through trace 7. So if I just want to show you this before we call it a day. On trace 8, it's going to try to do the forward SIGINT only to the foreground job, but we had to do it to a foreground job to begin with. So I couldn't think of a way to isolate these two together. So once we're done trace 7, we should actually be done trace 8. But we're going to confirm that right now by just checking our tiny shell. So we get 2 points for trace 1, 2 points for trace 2, 2 points for trace 3. if you can find a non-hacky way for you to get trace 7, but not trace 8, let me know. And I'll update the slides with the different implementation. Like I can force it by just like grabbing the 0th index of the jobs list, but that's a very hacky like that's me implementing to break it, not to do a naive implementation that I'm going to grow in capabilities. We can see, oh, I didn't quite get what I wanted here.
You know, this another set PIP with the it's like in the handout it had to do the right.
Oh, with the set process group ID? Yeah. Yeah, that's right.
You didn't do that. Would that cause it?
Yes, yes. And I was double checking to make sure that I had put it in my eval function, and I'll double check, but I'm out of time today. We will circle back and relook at the code, make sure everything is working as it should be. Check to make sure your string matches exactly though, because that's what's essentially just matching to the string that's coming from our output. But we'll pick back up at the tail end of trace 7. Once we're done trace 7, we should be done with trace 8 as well, which would put us about 40% through the shell lab, right? That because there's only 20 traces. Excellent. I will see you all next Tuesday.
Failed on the check, the Python check.
Yes.
Mine went through.
Yeah, I think it's a string error.
Oh.
I think I just didn't get my string error.